Now, something that's going to be important to you much later is Kirchhoffs Law and a couple other laws we're going to talk about right now. Thevenin's theorem, Norton's theorem, and superposition. Kirchhoffs laws, by the way, you've seen the little sticker that you can get from Mike Holt and a lot of other guys. It has 900 Ohm's law theories on it, Ohm's law formulas, right? And you don't need those anymore because you know Pioneer and the two laws you derive from that. And you can get anything from those laws right there. Pioneer, and then the two derived formulas, P is equal to I squared R, and P is equal to E squared over R. So with those, you can do anything. But I want to tell you that George S. Ohm only said one of those things. So where are all those other formulas come from? Kirchhoff, or Kirchhoff, depending on who you're talking to, is the guy that decided, well, if that's true, and he doesn't get much credit for that because it's still called Ohm's law instead of Ohm's singular law and Kirchhoff's interpretations of those, but that's a whole different opera. So anyway, we're going to describe Kirchhoff's voltage law and his current law. And they both basically say the same thing. What comes in must go out. It can't hang around. You can't have leftovers. You can't have stuff staying in something unless it's a capacitor. Let's see here. Reduce a circuit to a single Thevinin equivalent circuit. Reduce a circuit to a single Norton equivalent and solve a circuit using the superposition theorem. Those are the three main things we're going to learn about in this. The algebraic sum of the voltage sources and voltage drops in a closed circuit must be. Now it says must equal 0, and they're assuming that the voltage supply is positive and all the voltage drops are negative, and it's got, in other words, they've got to be equal. Forget sum to 0. They've got to be equal. Okay, what comes in must be what's supplied. I mean, what's dropped across these places must be the total of the supply. You already know that. Algebraic sum of the current entering and leaving a point must equal 0. What comes in has got to go out. Unless it's a capacitor, whatever comes in has got to leave that point. We'll talk about that in a minute. Okay. Okay, here we have an example. This is a pretty simple example, though, of where we have two resistors, and we have current flowing through them and going out the other way. Now we've got 6 amps in this bottom resistor and 4 amps in the top resistor. And if there are only 3 wires coming to this junction point right here, whatever's coming this way plus whatever's coming this way have got to add up. Because what comes in has got to go out, right? The same thing is true if we're going the other way. If we had 10 amps coming into this thing and we had 2 resistors, all that current's going to be going out through those 2 resistors. That's all Kirchhoff is saying. So it's a pretty simple rule. Now, I want to make a little drawing here because we don't usually have just 2 in and 1 out. Well, actually, that's what we do usually have. But occasionally, we'll have a network where we have a single point, and we might have, let's say this is line 1, and line 1 is going through a resistor, and it's coming down here to this point right here. And then we're going to come down here, and we've got another resistance, and we've got another node or junction, and we've got a resistance there. Now, line 2, we're going to say is a different, it's a voltage that's happening at a different time. And that doesn't mean a great deal, except that we're going to measure the resistance coming here. Well, let's not do that. Let's not put it there. One more time. Now, one more thing. From this point, in AC, you might have a line 1, a line 2, and a neutral point. And when you have, well, we won't get into that for the moment, but let's just look at, we could have current flowing from 2 different places. Let's say we have, 5 amps coming this way. And let's just say that 3 amps are flowing down this way. And 2 amps are flowing this way. All right? Now let's also look at, on the other side, we have 10 amps coming this way, and let's say we have 5 amps coming in here. And we also have 5 amps coming in here. Okay, now, I've left a line out. We have a line between here and here. Now, Kirchhoff says whatever comes into this network, point, this one right here in the middle, has got to be equal to what goes out. So if we have 5 coming this way and 3 coming that way, we're going to have a balance. No, we won't have 8. In AC, it's different. But in DC, let's talk about just with batteries. If we have just a battery, it gets a lot simpler because AC and DC are completely different. So we're just going to stick with 2 different batteries with the same negative point. So these are both positive, and so we will just have additive current. But first we have to look at what's going on down here. What's going to go this way? If it's DC, we're going to have 7 amps coming in this way, right? Everybody agree with that? Okay, we've got 7 amps coming that way. Now, we know we've only got 3 amps coming in from the top, right? Coming in here. Everybody agree with that? And coming in the bottom, we're going to have 5 amps. Everybody see that? Okay. So how much current's going to go back down this green thing? Well, as long as we're talking about just DC, yeah, it might be 15 amps. But I want you to realize this is going to really change when we're looking at AC. Okay? There's a big difference between DC and AC. Now, DC, whatever goes out this line and that line has got to come back on this line as a total, right? And we're not going to talk about AC just yet, but this is going to become a real important thing when we talk about this in AC, because this is something that happens all the time. We've got to figure out, okay, part of this stuff in the red balances out part of the stuff in the blue, and what's left over has got to go back down the green, and that's what this is really all about. We're not ready to talk about that because we only want to talk about DC right now. Okay, but I want you to realize that what Thevenin's really talking about is useful for DC, but it's really, really important in AC. Okay. Kirchhoffs voltage law or Kirchhoffs voltage law. We've seen this someplace. Where have we seen ET is equal to E1 plus E2 plus E3 plus E4? That's Kirchhoffs law. That is his law. That's his rule. He developed that idea. Okay? Current sums of voltage sources and voltage drops in a closed circuit must equal 0. What comes in must equal what is supplied, right? If you've got a current, and now in a series circuit, it's all constant, so it really doesn't help you much, right? So realize that this is probably talking about parallel circuits, because parallel circuits are current dividers, right? So the supplied current must be the current through all the different circuits, branches of the circuit. Okay? And here we have a combination problem, and it can be solved with Kirchhoffs law and superposition. Algebraic sum of the voltages around any closed loop must equal 0. All right. Okay, Thevenin's theorem simplifies circuit into an equivalent circuit which contains a single voltage source and a single series resistor. So, when we come to combination circuits, we're going to be using Thevenin's theorem, which is we can simplify anything into a single series resistor. And it doesn't matter how complex it is, we can simplify it into a single series resistor and a single voltage source. All right. Thevenin circuit consists of a single power source and a single series resistor. Well, that doesn't show you a good example, but when we get to, I can guarantee you, when we get to combination problems, it will become very evident what we're talking about here. Okay. Norton's theorem is kind of like Kirchhoffs law, but only different. It's used to reduce the circuit network into a simple current source and a single parallel resistance, which in certain kind of circuits is very handy to do. Most of our combination problems we will simplify with Kirchhoff's law. All right. Superposition. Any branch of a circuit supplied by a multi-power source can be determined by finding the current produced in that particular branch by each of the individual power sources acting alone. So you could look at, when you're looking at two different batteries, for instance, that are hooked up opposing each other, going through a couple of loads, you might need to look at how much current is going to go each way individually to find out what's going on. Okay, here's an example of having two different batteries. You notice the positive is at the bottom of both batteries, but we've got three different resistors, and we could resolve each part by looking at the current that would happen in each branch and then add those ideas together. Okay. And finally, we got one done in less than 15 minutes. Now I want to know what it takes. Just don't have very much content. Okay, let's stop this.